Echo 4 Bravo Delta Echo here. Today I'm going to show you how to properly terminate a PL259 connector or a UHF connector onto an RG8U cable or LMR 400 or similar diameter cable. Some of you might remember from my previous video there where I did the building the dipole and when I strung it up on the roof. About probably 3/4 of the way through the video or so, I was salvaging some coax for the feed line, and I pointed out the poor termination on the end of the cable where the braid was showing on the outside of the connector there, lacking the strain relief. And well, the majority of it was majority of the connector was terminated properly, soldered on the body. Center conductors soldered and not crimped. Some guys like to crimp them. I don't know why, but they do. Because the braid was sticking out past the connector, there was no actual mechanical strain relief on the cable. So I'm going to show you how to properly terminate this, and I'm going to kind of go step by step and kind of give you the steps that I took when I was learning to do this. For some of you out there that this might be, maybe the, first time, or, maybe you've tried it a few times and failed, or you're having some trouble with it and looking for some tips kind of thing. So I got a couple chunks here of RG8U. They're, roughly about 2 feet, just over 2 feet long. I'm going to be making a couple patch cords for my switch. Some of you might think that this is that this looks like a pretty garbagey, crappy cable. Don't mind the workshop, by the way. This is what happens when I do project after project back to back and don't put any time aside for actually tidying up and that kind of thing. And normally I wouldn't go and show this kind of thing on YouTube or whatever, but it's just gotten to the point that it's like, well, you know what? This is just how it is, so people are going to have to deal with it. And I'm sure I'm not the only one here that's got out here in the electronics or the amateur radio hobby that's got a little work surface area that looks like a bomb went off on it. So just deal with it. Anyway, yeah, some of you might think that this cable looks like it's more or less garbage or worn out, but actually it is salvage cable, but inside it is like nearly perfect, nice shiny copper. There's no corrosion on it whatsoever, and it is very good, high quality. I don't know if you can read that or not. It's very good, high quality Belden cable, so it's not like it's a cheap Tandy or something like that. I've used the Tandy stuff and it's not bad, but the Belden stuff, the shield, the way they braid the shield and stuff on it and everything like that is significantly higher quality, and there is more manufacturing tolerances involved in some of the higher end cable like the Belden, as opposed to some of the cheap cheaper Archer or Tandy or Radio Shack RG8U that you might find lying around or for sale at the local ham shop. I've got a good fair chunk of that stuff too, but it does what it needs to do. So yeah, the cable is very good internally. It's just fairly weathered on the outside, but I've been using this for all my patch cords. I got a couple chunks of it. I can't even remember where I got it. I don't remember if I got it out of the classifieds or if I got it from the local flea market or not, but I've been using it for most of my jumpers, and it is good cable, so I'm just hanging on to it. And I just can't justify buying brand new coax when there's all of this great usable coax out there that some of the operators they're kind of like, oh well, every so many years I'm just going to replace all my feed lines kind of thing, even though the cable is perfectly good and there's nothing wrong with it. They rerun all their coax, replace all their feed lines, and well, then people like me, the salvagers, we can take advantage of getting good quality, used cable. If you don't mind the fact that it does look weathered and used and a little bit worn out on the cable jacket, you get a great cable for next to nothing, and sometimes even free. Um, so, um, I've kind of drawn out a quick, few minute sketch of a cross section of a PL259 connector. So I don't know exactly what the proper terms are for the two sections, but it is a two-piece connector. I call this piece here the main body, which is this piece here. That's where you actually terminate your coax to. You actually make the physical and electrical connections to the connector. And this, I just call this the retention ring, because that's literally all it does, is it retains the main body of the connector onto your SO239 when you thread it onto your radio, or your antenna, or your switch. So as I was mentioning, there was no strain relief on that cable that I showed in the other video, and that's I mentioned the threads. And yeah, if you look inside the connector, there are threads on the inside of the connector, and they're designed to actually bite onto the jacket of your coax cable. There's also adapters that you can use that will reduce the size for like the diameter of like an RG8X kind of thing. And what you would do is you would there's some threads on the back end of that adapter, and it's flat on the top, so you would strip it. You'd wrap your shield around the front half of it on the outside of the threads, and that metal, I don't have one to show you right now. I used the last one on a chunk of cable that I made for a 30-foot chunk of cable I made for field testing with my antenna analyzer. But it's a piece of metal that's hollow in the middle, and the cable slides through it. You wrap your braid around the outside of it, and the metal kind of holds the braid up towards the edge of the connector, so you can actually solder the braid. And you do want to solder the braid. Some people don't. They just use friction fit, but that's when you're going to get corrosion issues in there if you do get moisture. And that's assuming the corrosion doesn't get into the coax itself. But you want to solder at least one of the little holes here. You want to solder at least one of the holes, so you have a decent connection to the shield of the cable. Otherwise, when you first install the cable, it might work great, and after a while it might be intermittent, or you might get a high SWR, high losses. So yeah, basically these threads here, you actually physically thread this piece of the connector onto the jacket of the cable, and it creates a mechanical strain relief on it that'll take the strain off of the solder connections on the shield, and mostly take the strain off of the center conductor, which if you overflex it, it can become brittle and break, especially when you're stripping it. If you happen to accidentally nick, and a lot of times most people do, they'll accidentally nick the copper a little bit there when they're stripping it down, and then naturally you solder the center conductor here as well. The PL259 is also called a UHF connector. The main reason they call them a UHF connector is because they were designed back in the 30s, and in that time, anything over 30 megahertz was considered ultra high frequency, and the terminology kind of changed, but the name for this connector just kind of stuck, and it's kind of like one of those as per convention kind of things. Just like you have let's say, for example, DC current, positive and negative, and per convention, when you're looking at diagrams and stuff like that, and doing formulas and solving the circuit, per convention, the flow is from positive to negative, but in reality the current actually flows from the negative side to the positive side. So it's just another one of those kind of abnormalities that somebody named it before there was really an official standard for the specific name, and as per convention, it just kind of took hold and stuck. So when you're stripping the cable here to solder these connectors. These are cheap connectors. These are probably the cheapest connectors that I was able to find. They were about $3 each after tax. These ones have a bakelite insulator, and that's this little piece right here that holds the center conductor away from the outside body of the connector. And they're typically made of, Teflon, nylon, bakelite, and they all have their pros and cons. Nylon is, probably the least desired material because it's not heat resistant. It is cheap, and a lot of the connectors with the nylon in them are going to be like the cheapest quality connectors you can get. But the issue with those is that when you start soldering the center conductor here, if you put too much heat onto this, you can cause that Teflon to melt or soften and deform, and you can cause that conductor to turn and become crooked or to migrate, and it can cause issues with the impedance or with being able to mate that connector with a proper terminal later on when you go to plug it into your radio or something like that. The Teflon is probably Teflon and bakelite are both good. Teflon is a little bit more flexible than bakelite, and is also heat resistant, so you can give it a little more heat before it starts to melt. Bakelite is more heat resistant than Teflon, but it is very rigid and brittle. And bakelite is a plastic that was designed in the early 20th century, so around the 20s or 30s or so. It was one of the first commercially available plastics that the average homeowner could go out and buy something that was made of plastic for their home. One of the huge benefits to the bakelite was the fact that it was highly heat resistant. So, for example, back in the 30s and 40s and stuff like that, when all your radios ran on vacuum tubes or valves or whatever you want to call them, they produced a lot of heat. And prior to bakelite, there was the sockets that the tubes sat in were made of porcelain or ceramic, and they were expensive and difficult to make. When bakelite was invented, and actually I should mention here that it is actually pronounced bakelite, though due to its spelling, a lot of people pronounce it bakelite, and I kind of sometimes jumble back and forth between the two pronunciations of the word. But when bakelite was invented, and due to its superb heat resilience, they were able to start making these sockets out of bakelite instead of ceramic or porcelain, and it reduced the cost. They also started making the cabinets of radios out of it, and you can always tell bakelite from other plastics and stuff like that, even when it's polished, is it does have a very dull kind of unrefined look to it. Even when it's polished, it doesn't look as shiny or perfect as some of the other plastics that we know today, like some of the polyethylenes and polypropylenes and that kind of stuff. So you can always tell the bakelite from the Teflon, and the bakelite is always usually going to be like a brown or a black or a darker color kind of thing. You might get some kind of like a cream color kind of thing, but you're never going to see that bright white or that semi-translucent, that translucent white like the Teflon or the nylon. Just food for thought here. This is actually the chemical name for bakelite right at the bottom here. I don't even think I can pronounce it. Polyoxybenzyl methylene glycolinhydrate. That's a mouthful. So if you're able to memorize that, and you ever want to stump somebody with a tongue twister, try and get them to pronounce that word. But that is actually the chemical name for bakelite, which is actually a thermal setting phenylformaldehyde resin, and it has to do with I can't remember exactly what it is. It's like the removal of phenol with a reaction to the formaldehyde kind of thing. I can't remember exactly what it is, and it forms a resin, and it is a thermosetting resin, which means that with heat, it is when you're setting it, it it the heat causes it to actually set in its form, and yeah, I don't know exactly 100% the chemistry behind it and everything like that, and I could be wrong with what I'm saying here, but that's basically more or less what it is. But it was one of the first early plastics, and these are one of the cheaper connectors that aren't complete garbage like some of those like $1 or 50-cent ones you can buy, eBay kind of thing, Chinese surplus garbage, and those are usually like very, very thin, like nickel coated aluminum or something, very soft body. Like I've had connectors where I've gone to twist them onto a piece of coax, and you grab the outside here with pliers to twist it onto the cable, and it shears off where the holes are here. And yeah, some of them are really soft garbage, and they use like the crappiest nylon that you can put in there. You stick a soldering iron on it, and immediately the pin starts moving around all over the place. And stick away from those if you can. And eventually, when you're able to identify the the insulator, and you can tell just by the thickness, like the gauge of the metal and stuff like that, you can tell a connector just by looking at it if it's going to be a decent enough connector. It doesn't necessarily have to be silver coated or something like that. Those are a little bit better for the higher frequencies, but again, if you're going to be going and trying to use a connector to connect to a UHF radio or antenna, you're better off using like an N-type connector or a TNC connector or a BNC connector, or even BNC's kind of getting there on the low end of the spectrum, or an SMA connector. They're significantly better than these old relics that were designed back in the late 20s, early 30s. For the higher frequencies, they're more or less useless. You're going to get significant insertion loss from these connectors. But when you're talking a couple hundred megahertz lower, like especially in HF, like where I'm operating, 30 megahertz and lower, the losses are going to be negligible with a properly terminated cable. So the next point here, now I got all this crap aside and I'm done with my rambling and little tidbits and stuff here, I'm going to start showing you how to actually terminate this cable properly. I'm going to go step by step and explain to you. I'll give you the rundown of how I'm going to do it first, and then I'll cut it back and explain as I'm going how to terminate this connector properly. Obviously the first thing you're going to want to do is you're going to want to measure and cut your cable. And part of the thing you want to remember too is when you're measuring your cable is not just a physical length, but these cables also have a bend radius on them. And every manufacturer is slightly different. A lot of it depends on what the material is for the dielectric. Like this is, like it's a solid dielectric. Some of the cables have like a foam dielectric in them, and I actually have a piece of junky cable here. This is like garbage tan. This is like the garbage of most garbage RG8 you can possibly get, and I'll show you this a little bit later. Like look at the shield on that. Like that's like what, 40% shielding on there, and that's actually was copper, but that's all corrosion. Like it's all the way through the cable. Like I was cutting this back when I was looking for a chunk of cable, or one of my last projects, and like even the center conductor is just black with corrosion all the way through this cable. It's just junk, and it's a foam dielectric, and you can tell the difference just by holding this. This is like, this chunk of cable here weighs almost half what this Belden weighs. But what the bend radius is it has to do with putting stress on the cable, because when you're bending it, you're going to have compression underneath on the inside of the radius and stretching on the outside of the radius, and the conductor inside the coax is going to want to move along with it, and what ends up happening is it migrates towards the center of the radius, because the copper is not going to stretch as much as the plastic. This is called center conductor migration, and it'll cause the cable to stray off its impedance characteristics and stuff like that. And I've had cables that had such bad center conductor migration that they've actually almost shorted out to the outside sheath, and started attenuating the signals to the point where at the other end of the cable there was like nearly nothing there. So this bend radius, and every manufacturer is going to be slightly different, but it's usually some kind of a ratio, very simple, like mathematical formula, based on the outside diameter of the cable. So like it might be, for example, this particular cable here is roughly 10 times the outside diameter is the bend ratio, and it ends up being about 4 inches for the radius. So I can have a 4-inch radius on the bend without putting too much stress on the cable, and that's unloaded. That means there's no weight or anything on it. Now if it's, say you have a connector hanging at the top and you're bending it down and that cable's weight is pulling down on it, you're going to have, this is a loaded, it's got load on it now because you've got stress on the cable. There's going to be a different coefficient for the loaded radius, bend radius, and it's usually a larger radius. So just things you want to keep in mind when you're cutting your cable to length. And just for a little bit of fun here, what I'm going to do is I'm going to bend this. I'm going to wrap this with a bit of tape here. This is severely over the bend radius, and what I'm going to do is I'm going to let it sit here while I terminate this cable and do this video, and then at the end of the video we're going to come back to this and I'm going to chop it in the middle, and I'm going to see here, and hopefully we'll get a little bit of center conductor migration, because this is like the crappiest foam center dielectric that you can get. It's very soft, so hopefully we'll get some center conductor migration. I'll show you exactly what I'm talking about when it comes to that. Ready to terminate the cable here. We're going to start by stripping it back, and one of the things that I'm going to recommend for everybody who's just beginning to do this, or maybe they've done it a couple times, not very good at it, or whatever. If you're not familiar with how to do this, line it up with your connector. And the initial step here, you don't have to worry about this right now, but the initial step is you're going to strip through a good chunk, because you're going to want the inside conductor, the center conductor, to protrude through the end of this, through the end of the connector here. And it doesn't matter, it can be, half an inch and a half, whatever. You're going to trim it off after. So you're going to want to strip it back, but you're only taking off the outside jacket and the shield, and just leaving the bare dielectric. And that's going to be the first step. The next step from there is you're going to move up from the edge of your shield about, like, I don't know, maybe 1/8 of an inch or so, a few millimeters. And you're going to move up from there, and you're going to strip off your dielectric to expose the center conductor. And then this is where you're going to want to line it up, because you're going to see how much shield you want to expose. So you're going to, wherever your dielectric ends and the center conductor is exposed, that's going to basically bottom out right in this area here on the connector, where the Bakelite insulator or nylon or Teflon insulator is. And you're going to basically expose the shield here, right? And just so that it's underneath the where the holes are, because that's where you're going to solder to make your electrical connection to the shield. You want to have a good chunk of the jacket covering this range here, because that's all thread, and that's designed for mechanical strain relief for the cable. So I'm going to go ahead and I'm going to go step by step. I'm going to show you exactly what I mean by stripping this down. I don't have a tripod or anything for this camera, so I'm going to have to pause the video here and strip it back, and then I'll show you exactly what I'm talking about step by step as I go ahead and do it. Okay, so here is the first step, as I mentioned. You can see I've done all 4 ends, mainly because I just like to do it this way and just, make the process a little quicker when I'm doing, multiple cables kind of thing. And you can see what I mean by I strip back the jacket and the shield, just leaving the dielectric. And now, what I'm going to do is I'm going to go and move up a little bit, leave a little bit of the dielectric there, and expose the the center conductor. And if you see here, once this is all in the cable and bottomed out and everything, I'm going to have like 1/2 inch of at least of the center conductor sticking out the end of this connector, which is ideally the kind of thing that you want, because a little bit more is better than nothing. And then get a good solid solder connection at the end of here, and you just snip off the excess at the end. So the next thing, I'm just going to bare these center conductors with a little bit of the dielectric showing, and this is kind of what I'm talking about here, because if you look here, I don't know if I can get a focus on that. The damn camera's acting up here. You can kind of see it glinting there a bit, but there it is. You see that few strands of shield there sticking up? That's one of the main reasons why I leave that section of the little piece of dielectric sticking past the shield, because if you get a long enough chunk, it could migrate over and create impedance issues or short out to the center conductor. You know, ideally I'm gonna notice that, so I'm gonna you know, cut that off before I actually go and terminate that. I'll also point out that this is my weapon of choice here for stripping these cables. You can, you know, buy all kinds of fancy coax strippers and stuff like that, but you need different strippers for different size coax, and when you're doing all different sizes like 8U, 8X, RG6, 59, 58, and you know, you name it, LMR 400 and everything, the outside diameters are different, the dielectric diameters are different, different shielding, everything like that. You either need like a really fancy specially adjustable thing, or you can just figure out how to do it by feel with a knife, and it just makes it easier, because then you can do any diameter you want. It doesn't matter how small or how, you know, how thick diameter the coax cable. If you know how to do it by feel, you can just use the same tool for everything. And like when you're doing the outside shield, as you apply some pressure, you're gonna cut through the do a, you know, a complete turn around here, and you'll cut through the jacket first, and then it's nice and smooth. Then you add a little bit more pressure as you're cutting through the shield, and you almost hear like a crunching sound. And you go slowly, and as it cuts through every single one of the copper pieces here, you hear almost like a crunching sound. And then once you go back around, a little bit less pressure, and you're gonna want to, you'll get a feel for it once you get used to using it. It's hard to describe, but you'll feel drag on it when you get to copper that hasn't been cut through, and you can apply a little bit more pressure, and you'll hear that crunching sound again as it cuts through it, and eventually you'll, you know, it usually takes 1 or 2 wraps around the cable there, and it'll just feel nice and smooth without putting pressure on it naturally, because otherwise you're going to keep cutting deeper and deeper into the dielectric. And that's when your copper shield is cut through, or majority of it's cut through, and then you might have a couple strands here you got to deal with after. But you do it all by feel, and you get used to it after you've done, you know, a handful of these things, and you'll know exactly how it feels when you're twisting the knife around the outside of that cable, and you can feel the drag on the copper, and you can almost feel it snagging as it's cutting through each individual piece of copper there. And you know, you'll get used to it, and you'll know how much pressure to apply and when to back off on the pressure, and you know, if you screwed up and gone too far, and you've just got to chop it off and go again. And you get used to it. It's one of those things that you know, you're not going to know right away. You got to actually do it, try it to get a feel for it. But yeah, that's what I use, just a, you know, run-of-the-mill utility knife kind of thing. I've actually used like paring knives and steak knives and stuff before too, in a pinch. Like when I was out at the lake doing an antenna out there, we didn't have a utility knife. I used a steak knife, and it worked just as good. Okay, so got the center conductor exposed, and you know, just as I was explaining, a little bit of the dielectric between where the shield is going to start and where the center conductor is. It's just kind of like an insulating buffer, just you know, additional short protection kind of thing there. It's just good practice. It's not necessary, but I recommend it. Some of these dielectrics, like this one for example, I actually struggled with these a little bit. They can be pretty difficult to get off, so after you cut around the outside of them, circular, what I find helps is to cut lengthwise on two sides and kind of peel it off in two halves, as some of these are like literally like plastic, like they're melted onto the conductor as it's passing through like an extrusion machine kind of thing, and it makes it extremely difficult to get these things off. And if you do try to get them off without cutting lengthwise, the best thing to do is to go with the twist of the cable as you're pulling. You can see the that's what I did to my fingers. They're just pulling on the dielectric, but twist with the twist of the cable, and it'll help. It's almost like once it gives way, it's kind of almost like unthreading a nut off of a screw, and it'll go a little bit further, but a little bit easier. But if you look inside, like the dielectric here, you can see, if I can get the camera to focus on it, you can literally see how it's like directly molded to the cable, and you can see how I slit down the one side of it to help kind of pry it open and release the pressure so I could pull it off. Especially when you're doing short runs of cable like this, because if you just try and yank on it, what you're going to do is you're going to pull the whole thing through, and you're going to actually pull the dielectric into the one end of the cable and out further out the other end. And even though I was being careful with this, I actually did pull a couple of them a little bit too far, and I had to grab the pliers and pull it back, tug it back through the other end, and straighten it up a little bit. Just, it's amazing how much force you have to put on some of these dielectrics to get them off the center conductor here, and it can actually pull the whole thing, the whole dielectric and the center conductor, actually through the shield on the inside of this cable. And if you're not careful and you cut off too much and everything, you can end up with your dielectric like way in here. And yeah, so that's just one thing to keep in mind as you do that. So the next step here is just to, this is where you're going to probably want to, if you're not familiar with it, line it up with your connector, because that's roughly where your dielectric is going to end on the connector, and where your center conductor is going to protrude from the end of the center conductor on the connector. And you want to bare the shield about that much, and that's being Canuck and all, that's roughly about a 1 centimeter. So you're just gonna give or take roughly bare that much, and that'll give a good chunk of the jacket of this cable here to actually thread on the inside of this connector to give it strain relief, and the shield will be bared here for electrical connection. And from there you just thread the connector on and solder it all up. So there's the cable stripped and ready to go into the connector, and you can see I've got it lined up with the connector here, and you can see where the shield is going to be lining up with the holes here for soldering. The jacket is significantly good, majority of the threads of this connector over the jacket of the cable for a good solid mechanical strain relief. And I got a bunch extra center conductor sticking out the pin so I can solder it nicely and just clip it off neatly at the end. When you strip just the jacket off here, once you've gone through all this and everything, you might be gung-ho and just putting too much pressure. You want to be light with it. Just enough pressure to, it's almost like cutting flesh, cutting skin. Just enough pressure, and once you break through it, you almost back off the pressure because it just glides through it as you're cutting through it. And I again cut a circular score around the edge of the cable here, and then along the cable, so I could just peel it off like that. And you can see again how they just kind of extrude everything around it. You can see the actual markings from the shield on the inside of the plastic here. So it's it's all extruded in the machine. It's all liquid. It goes on. So everything's like nice tight fitting and everything like that. Another thing you might want to do is just grab the cable after and just tug on the shield, just to, when you were stripping it, you might have, all these little pieces here, you might have severed some pieces of the braid, and you don't want that getting loose inside that connector, because you'll end up with, a short or something like that. So, you know, just kind of play with it a little bit and tug out the, see, one of them just fell out there, and get the loose pieces out of there. And then you just thread the connector on. Little pliers are good to have, because sometimes, depending on the manufacturer, they'll go on nice and easy, you know, finger tight. Some of them you might have to give them a little bit of pressure to twist them on. So pliers, always grab here, never grab these threads, because these threads, the threads on the inside of this connector actually thread over top of this. So if you damage these threads, you won't be able to get the ring over top, because those threads will be screwed, and you just wasted a connector. So I've got all the connector bodies threaded onto the coax, right onto the shield there. This cable is actually nice. I was able to do it by hand. It didn't need pliers at all. You can see through the hole. You can see how nice and visible the shield is, and this is where you're going to solder the shield to the connector body, and you can see the center conductor is protruding past the edge of the connector. Now that's what you want. You're going to solder it nice and then just clip it off right at the edge there of the connector on the PL259. Now, soldering these things, what you're going to want to do, don't just take your iron and jam it in the hole here and start heating up that copper and everything like that, because all you're going to do is you're going to melt the dielectric. You're going to force that copper towards the center conductor and just totally screw up the termination. This iron is actually a little bit underpowered for this, so it takes me quite a while to do it. I got to heat this connector body for a good 3 or 5 minutes or so, but heat the connector body first. Apply some solder so that you get better surface area for heat transfer, and wait until the solder starts to flow and wet to the connector body. Once it does, then you can move it over here and apply heat to the shield and add some solder, and you'll get a nice solder connection. You only really have to do one. I like to try and do 2 of them, and then just once that's done, solder this and just let it sit till it cools off. And these things can stay hot because just because of the mass of this connector. I mean, I was just touching with the iron already. It's already warm. Like I can feel it in my hand. It's warm already. And all the copper in here, like it retains heat quite a bit. So this thing will probably stay too hot to the touch, to the point where it'll burn you for a good 5 minutes or so. So just leave it, let it sit, and whatever. Make sure you put your rings on here, because once these ends are soldered onto the cables, unless you're good at pulling these things off, desoldering them, and reusing them and salvaging them, you've got a shot useless piece of crap connector that you can just chop off and throw in the garbage. Maybe someday when I get a decent setup here with tripod and stuff for this camera and everything, because I frequently reuse and you know, repurpose and salvage these PL259 connectors when I'm in a pinch. Maybe I'll do a little run through on how what I do to actually repurpose these things. And you know, sometimes I got to run a drill bit through the center conductor to clean them out and everything. But yeah, yeah, maybe that's a future video. But yeah, so I'm going to go ahead and solder this thing, and then I'll show you exactly what it looks like once it's soldered. So I've got the connector all soldered, and I got one nice solder joint on this side. This side didn't turn out too great. I'm gonna have to touch that up a little bit. It kind of stuck out a little bit past there. Just melt it back or snip it off or whatever. But just to give you an idea, I got my infrared thermometer here. Show you how hot these things stay. It's not really picking it up here. It's saying about 70 degrees Celsius, which is, it's quite a bit hotter than that, because like it hurts to touch it. So the thermometer is just not picking it up that great, because it's a reflective metal. I move it down to the edge of the cable here though, and it's jumping up quite a bit. It was almost hitting 100 there, but yeah, it's make sure you let them cool down after you finish soldering there. And I'm going to touch up this end here a little bit, and just have to flatten it out because it's so that the ring can thread over top of it after that side connection. I'm not overly proud of it, but it is soldered, and I do have a nice, perfect solder connection on that side. You can see how nice that one is, as opposed to this lumpy piece of crap on this side. But it'll do. And the center conductor is soldered, and I just have to go and clip that off there. And yeah, that's it. I'm gonna go and I'm gonna solder the rest of the ends of these cables, and they're ready to go. They're ready to be installed. So the cables are all terminated, nice and complete, and the last thing at this point is just to grab your multimeter, and I've done this off camera already, and just from end to end do shield to shield on the body of the connector in resistance or ohms mode, just to look for a very, very, very low resistance, to make sure that you got a good connection on both connectors. Same thing with the center conductor, both ends, and then finally between the shield and the center conductor to make sure that you've got an open or very high resistance, or depending on your meter, if you got a crappy meter, you might show a very high resistance, but you should show like an over limit, or like just infinite ohms between the two, and that'll tell you got a good connection between this end of the cable and this end of the cable, and no shorts internally. It won't give you any feedback on the impedance or anything. You'd need to get in a little more depth, but at least that way you'll know that you're not going to plug this thing right into your radio and directly short out your antenna output. So there you have it. There's two nice roughly 2 foot long patch cords that will go into my antenna network. And last but not least, over here, if you remember earlier from the video, I had my chunk of cable that I said I was going to wrap up with the tape and in a tight radius, and you can see on the outside here how it's kind of stretched the text on the outside of the cable, and how if you look closely here that it's kind of squished this way, but if you look this way it's wider. Think of it kind of like putting a kink in your garden hose. So with any luck, I'm going to take these cutters here, I'm going to cut it right in the middle, and with any luck we should see some coax migration. Look at that right there. It's been sitting like this for maybe an hour and a half, 2 hours while I've been filming this video, and my camera does not want to focus on this at all. But if you look closely here, you can see how the center conductor has already begun migrating towards the inside of the radius on this cable, and that's just over like an hour, right? Like if you had done a sharp radius on this cable and just left it and considered it a complete installation, that conductor could have migrated quite a bit more. Like on this side here, a little bit of that was probably pressure from the cutters too. But look at that, look how that's migrated over already, and that's just been 2 hours on both cables. Like yeah, see how that's migrated already? A little bit's probably from pressure from when I cut it open, but still, like 2 hours and you've already got migration like that. It's even from the cut, it doesn't look like too much, because it looks like it's cut pretty flush with the dielectric. So 2 hours and you've already got migration in the
from the center conductor. So yeah, you want to make sure you don't overbend your cable when you're routing it. So that's all, and hopefully you enjoyed the video. Victor Echo 4, Bravo Delta Echo, clear.